Hello everyone and welcome to week 9 Math 2. We're talking about derivatives and what you can tell about the graphs. So for example, suppose that I have this graph and I'll just call it f of x. And you can see that right here at x equals 1, there's something that important that happens. That's when it gets to the bottom of this little trough right here. That is called a minimum, which I usually just abbreviate min for minimum. And when you go to where x equals 3, it gets to the top of this hill, then that's a maximum, which then I abbreviate as max. So at those two places, we would have that the derivative is equal to 0. So this week's lecture is going to have not a lot of theory, but a lot of examples. Because basically we need to find out where does the derivative equal 0, and then find out, is that a minimum on the graph or is that a maximum? One other thing to tell about the graph is as it's going this direction, it's going down. So that's called decreasing. The fancy word for going down, decreasing. And then as it goes from the minimum to the maximum, it's going up, but we call that increasing. And as you may have guessed, what I'm going to say next is on the other side, it's going down, so it's decreasing. Now, if I draw another number line down here and say right here is x equals 1, and right here is x equals 3, and you can write the x equals, or you could just write the number, that would be fine. And this is going to be about the derivative, not the original function. So right here when it's at the bottom, the derivative equals 0. Right here when it's at the top, the derivative equals 0. A couple of reasons for that. One is derivative tells you slope, and if you draw the tangent line right here, it would be a horizontal line whose slope is 0, which is what this is saying. The slope is 0. Okay, when it's going down, the derivative is negative. So over here, the derivative would be negative. I'm not even paying attention to what negative number it would be, but negative derivative means it's going down. And then positive derivative means it's going up. And then negative derivative means it's going down. So then when I finally write my answer and I ask you where is it increasing and decreasing, then you could write, so for increasing, and you could abbreviate it if you want, that would be between 1 and 3. So between 1 and 3. And where is it decreasing? Well, that's over here on the left from negative infinity to 1. So from negative infinity to 1, union, the right side, from 3 to positive infinity. So that's the increasing and decreasing. And now let's do some examples. So for example number 1, how about y equals x cubed minus 6x squared plus 8x plus 1. So in general, that picture that I just drew, so in general, this is what a cube function looks like, especially when you have extra parts like this. So basically this caused more curvature, so it's going to look something like this. So to find out where the minimum maximum are, then take the derivative and just use the power rule on each one. So for this one, it's going to be 3x squared. And then when you bring the 2 and multiply, that's going to be 12x. And the derivative of an 8x is just an 8. And then the derivative of 1 would be 0. And then set that equal to 0. So we're not plugging in 0, we're setting it equal to 0. And then because this has a 2, that means there's 2 answers. And the 2 answers are going to come from the quadratic formula. So x equals negative b plus or minus the square root Then b is squared minus 4 times a times c, and all divided by 2 times a. So that's going to start with a positive 12, and then plus or minus the square root. So a 12 squared, that's 144. And then this would be a 12 times 8, which is 96, so minus 96. And then the whole thing is divided by 6. And now let's take a 12-second break while I go and get my calculator. Okay, was that 12 seconds? Okay, now I'm back. Okay, I want to verify that I did that part right. 12 times 8 is 96. Okay, that's good news. Then or I actually might as well just do the whole thing and get the decimal answers right now. So I'll put parentheses and then 12 plus the square root of 144 minus 96, and then stop the square root, stop the fraction, and divide by 6. So one answer I get is 3.155. And then I'm going to redo the same thing with the minus in front of the square root. And then the other answer I get is a 0.845. And when you do the problem sets and things like that, then I do want you to show this work, taking the derivative, set it equal to 0, do the algebra to solve for x, and then we can use the calculator. And when you use the calculator, make sure you graph the original problem, not the derivative. So y equals, the original problem was x is cubed minus 6x is squared, and then plus 8x. I'm just trying to check, is there a glare on the screen of the calculator? Let me just, yeah, I think that's better. Okay, I got up to the 8x, then plus 1. And then zoom standard, and then hopefully we could see what's going on with the graph. Yeah, actually not bad. And it does look like the very first example that I had drawn. So I also want to plug these points in so I could find out what y equals, and I'll go in order. So let me just get some more space right here so that I can write this down. So you can just go to trace and plug in the 0.845. And so basically, so right here at the top, there's a maximum, and it's saying when I plugged in the 0.845 for x, then the y right there is 4.079. And when I plug in the 3.155, it says down here is the minimum, and that is when x equals the 3.155, and then y must be a negative, and it's negative 2.079. All right, the last thing to do is write down where is it increasing and where is it decreasing. So for increasing, so that would be this left side. So right here is the 0.845, and right here is the x equals 3.155. So for increasing, it's this left side, so that goes from negative infinity until the 0.845. And then union, on the right side, this is also increasing, so from 3.155 to infinity. And then for decreasing, so that's the middle part, so in between these two x values, 0.845 to the 3.155. Okay, so that's the idea with the first derivative. When the derivative equals 0, that's how you can find mins and maxes, and then you can write down where is it increasing and decreasing. But then let's do a couple more examples with the first derivative. So for example number 2, how about something with the product rule? Like y equals x squared times x minus 3 is to the 4th. So for the derivative here, use the product rule. So just as a reminder, the product rule, where's my product rule? There it is. So to take the derivative of a product, you take the derivative of each one, but you can only take one derivative at a time. So y prime equals, take the derivative of x squared, which is 2x, and then leave x minus 3 to the 4th alone. Next it goes plus, this time leave x squared alone, and now take the derivative of this function, which means I need to put the 4 in front, and then subtract 1 from the exponent. And then technically I'm supposed to also do the chain rule. The derivative of x is 1, so then times 1. Now set it equal to 0. And with this one, it could be factored because this has an x and this has an x. So I know that I could factor out an x. This has x minus 3 and this has x minus 3. So I know I can factor out x minus 3. And the general rule is whatever exponent is smallest, that's what you can factor out. So I can factor out x minus 3 cubed. And then what remains? So this x got factored out, but the 2 did not. So the 2 remains inside. For these x minus 3 to the 4th, well, 3 of them got factored out. That means there's still 1 left behind. And then go plus. This 4 did not get factored out, so there's going to be a 4. One of these x's got factored out, but not both, so there's one x that remains. And then all 3 of these got factored out, so that's all that remains in the square brackets. And then there's x and x minus 3, and now I just need to simplify what's in the square brackets. And then when I do, I switch it back to round parentheses. So there's a 2x when you distribute, plus 4x makes 6x. And then distribute the 2 times negative 3, so that's going to be a minus 6. And now that it's factored, set each factor equal to 0. So the first one would just say x equals 0. The middle one would say x minus 3 cubed equals 0. And then 6x minus 6 equals 0. So with this one, you could cube root both sides, and it would still equal 0 on this side. After we get rid of that cube root, then just add 3 to both sides. And so we get the answers x equals 0, x equals 3. And for this one, you could add the 6 to both sides, so it's going to say 6x equals 6. So that number right there must be a 1. Or you could divide both sides by 6, and you get 6 divided by 6, you still get a 1. So it seems that the important numbers are 1, 0, and 3. And by the way, these are also called critical values, because there's something critical or important happening to the graph at those 3 points. And then let's see what it is. So let me get the original problem back on the screen and graph the original problem. So y equals, there's an x squared, parentheses, x minus 3 was raised to the 4th power. Now because this exponent is so big, it's most likely going to go off the screen. So when you graph it, at first we may not be able to see the whole thing. Yeah, so basically it's really tall and it's going off the screen. So to see where it is, I'm just going to put trace, and as you see it leave the screen, the cursor leave the screen, doesn't matter, just watch the Y values. So they went up to about 15 and then started coming back down. And then after that, it's just going to keep going up. So if I change the window and say, well, none of these are negative, so how about if I just cut this down to like -1? Because that way I'd still be able to see what happens at 0. And then we only have to go to 3, so maybe go to 5 to give it a little extra space. And then I'm going to change this to -1, and then here's the important part. It went to Y is 15, so I'm going to say go up to 20, and maybe I can see the whole graph now. And it basically looks like, to me, like a wonky W. So we have, this is the graph. And then this side would keep going up, this side would keep going up. And then we have x equals 0 is an important point. We have x equals 1, and we have x equals 3. Sorry, let me get that back on the screen. So x equals 0, 1, and 3. 0, 1, 2, 3. Okay, good. And then plug all of those values in. So when you trace and you plug in 0, so that's actually 0, 0. And I don't know if I have enough space. Let me try to write it right here. So that is a minimum. So at 0, 0, there's a minimum. And then this would also be a minimum. I'm pretty sure that's going to be 3, 0. Yeah, that's 3, 0. And at 3, 0. And then when it reaches the top, so this is when it reaches the top, the maximum, when you plug in a 1, it says it's up there at 16. All right, then the last part is, where's it increasing and where's it decreasing? So for increasing, so that would be from here up to here. So that's going up or increasing between 0 and 1. And then from 3 until forever, it's going to keep increasing. So union from 3 to infinity, it's also increasing. And for decreasing, that would be this left side. So that's from -infinity to 0. So for decreasing, -infinity until 0. And then also, as it goes from the top of the roller coaster down to the bottom, that's decreasing. So that's from 1 to 3. All right, we're done with that one. Now on to the second derivative and the graphs. So if you go back to that example that I had from the very beginning, it looked basically like this. And then I was talking about the first derivative. So right here, the first derivative would equal 0. Right here, the first derivative would equal 0. But if you take the second derivative and equal 0, that's going to be this point right here. So the second derivative, or the derivative of the derivative, equals 0. And basically what's important about that point is that this, up until that red dot, this is called concave up. So basically if it could hold water like a cup, that's concave up. And then this right side, this is like an umbrella that would shade you, protect you from the rain. I don't know why I said shade. I guess you could use it for shade. But anyway, this side is then called concave down. And when it's concave down, the second derivative is negative. When it's concave up, the second derivative is positive. So basically we're going to go through the same steps that we did previously, except we're going to take the second derivative instead of the first derivative. So for example, number 3, how about y equals x cubed minus 6x squared plus 8x plus 1. And you might be thinking, wait a second, didn't we just do that one? Yes, we sure did, but we did not find out where it's concave up and concave down. So we start by taking the first derivative. That's going to be 3x squared minus 12x plus 8. All right, we already used that on the earlier example to find minimum maximum. Now take the derivative of the derivative. So just use the power rule, and this one's going to be 6x. The derivative of 12x will be 12 with the minus sign. Derivative of 8 is 0. And then set that equal to 0. And then solve for x. So I could add 12 to both sides, making a positive 12 on the left side. And then all I need to do is divide by 6 on both sides. And then I have that x is equal to a 2. And then if you go back to that graph, let me just graph the original one again. X is cubed minus 6x is squared plus 8x plus 1. And then go back to Zoom Standard. So when I look at this graph, I would say right about there is where it changes from concave down to then concave up. Got a little mark on my calculator. Sorry about that, calculator. So that must be x equals 2. And trace, and you put 2, and then that's where it's changing from concave up to concave down. So basically this part is concave down. Then this is where x equals 2. And then this part is concave up. And the actual point where that happens, which is 2, 1, is called the point of inflection. So where it's changing from concave down to concave up, or the other way around, that's called the point of inflection. So then for concave down, so that's the left side of the graph. So basically from negative infinity until it gets to 2, that's concave down. And then concave up, that would be this right side of the graph. So that's from 2 to infinity. And make sure that I get all of that on the screen. So this part is concave down, and then this part is concave up. And now we're going to do one more example where we do all of those things together. So for example number 4, how about y equals e to the negative x squared? So usually I do the math first and then use the calculator, but sometimes I like to switch it up, so I'm going to do that here. What does this graph look like? Basically, all I'm going to do is get an idea of what the graph looks like, and then I'll still need to, or get to, do the math. So there's the e to the negative x squared, and then Zoom Standard to see the graph. And it's a short little function, so I think I should change the y values. How about if I range from -1 to +1? Could I see it better? Oh yeah, that was pretty good. Oh, that basically just looks like a bell-shaped curve. So in statistics, we call that a normal distribution or bell-shaped curve. And I'm pretty sure that right there when x equals 0, that's where the maximum is going to be. And now, time for the math. So first of all, with the first derivative. Well, the derivative of the e function is the e function, as I remember right here. The derivative of the e function is exactly itself. But then there's also the chain rule, so I do need to take the derivative of negative x squared, which is a negative 2x. Okay, there's the derivative. Now set it equal to 0. And the nice thing about this one is it's already factored, so all I need to do is set this equal to 0. And separately set this equal to 0. This one's going to be easy. All I need to do is divide both sides by negative 2, and on the right, 0 divided by negative 2 is 0. So yes, this point is at where x equals 0. And the e function never equals 0, so this one has no solution. So our only solution is x equals 0. And if I go back to the graph and trace and plug in 0, then that's at 0, 1. So there's a maximum at 0, 1. And then the left side is increasing. So for increasing, that would be from negative infinity until it gets to 0. And for decreasing, that would be the right side. So that's from 0 to infinity. And now we're done with the first derivative part. Now it's time for the second derivative. So then I need to take this first derivative and find the derivative of that derivative. And then just to be clear, I'm going to separate my work. Okay, so take the derivative of this. So the second derivative will equal, this is a product rule. So I need to take the derivative of the e function first of all. And the derivative of the e function is the e function. And just like earlier, I still need to take the derivative of this because of the chain rule. So multiply by negative 2x. And as far as the product rule, all I've done is this part. So I've only taken the derivative of e. Then I need to copy down the b exactly as it is. So then parenthesis, copy down the negative 2x. Then the product rule goes plus. Now just copy down the e function. And take the derivative of this. And the derivative of negative 2x is just a negative 2. And then set the second derivative equal to 0 and factor out whatever you can. So I notice this has the e and this has the e, so I could factor out the e. And I think that I'm just going to wait on the rest of the factoring. The important thing is getting this ugly blob, this friend, out of the way and see what's left. So when you multiply these two, that's going to be a positive 4x squared, and then it's going to be plus minus, so minus a 2. And as I said last time, the e function never equals 0, so you could put this equal to 0 and then say no solution, but since there's no solution, don't really have to do that. I just need to put this one equal to 0. So 4x squared minus 2 equals 0. And then add 2 to both sides. The next thing to do is divide both sides by 4. So on the left side, we only have x squared, and then 2 divided by 4 is a half. And then finally, to solve for x, take the square root. And when you do, there's actually two answers. There's plus and minus, the square root of a half. And as a decimal, what is that? So the square root of 1/2. So that's plus or minus 0.707. Now, when I first graphed it, I basically just, because I was talking about the first derivative, the only information I put was that there's a maximum right there. But then, ooh, this pen is leaking. Time for a new pen. Wardrobe change. So basically what's happening is, if you look at this part, this is concave down. So there must be a point right in here where this is concave up, this is concave up, then in the middle is concave down, and then this is concave up. So on this graph, I'm just going to put that information. So a point 707 plus or minus. So on this side is positive 707, and on this side is negative 707. And when I go to the graph and put in the 0.707, then it's saying the point of inflection right here would be 0.707, and then the y value is 0.607. And when I do it on this side, it should be negative 0.707. And because the graph is symmetric, the way that I drew it, it's not exactly symmetric, but this is symmetric. That means the y value should still be 0.607. And then let me test that theory, trace, and put in negative 0.707. And yes, it's the same 0.607. Okay, so there's the 2 points of inflection, and then where's it concave up and concave down? So sometimes I just abbreviate concave up. So this side is concave up, the middle is concave down, and this side is concave up. So for concave up, that would be the left side. So from negative infinity until you get to the negative 0.707. And then also the right side, so from positive 0.707 to infinity. And then that's the concave up. And for the concave down, that's going to be the middle part. So this is concave down between negative 0.707 and positive 0.707. Okay, then there's just one other example that I wanted to do. And this one is basically example number 5. So basically, what if you knew the information about the derivative and then also the second derivative? Then can you sketch the original function f of x? So let's say that for the derivative, you look at the number line, and at -2, the derivative equals 0, and at 5, the derivative equals 0. And then also it's known that here the derivative is positive, in here the derivative is negative, and in here the derivative is positive. So basically it's going up, down, up. And I basically just drew it, except there's a little more information, and that is with the second derivative, right here at 1, the second derivative equals 0, and then this is positive and this is negative. So basically with this information, it means that the graph is going up because of this being positive slope, and then down, and then up. And then right here is x equals -2, and right here is the 5. So that's basically what I'm reading off of this. And then as far as the second derivative, so 1 would be somewhere between there. Here's 1. And this part is saying that this is concave up, and that's, oops, I made a mistake. I can't believe it. After all of these years, I actually made a mistake. I switched these. Sorry, please fix this. These are supposed to be the positives, And these are supposed to be the negatives. Okay, so this part, when the second derivative is negative, that means that it's concave down. And then when the second derivative is positive, that means that it's concave up. So then can we put all of this information together and sketch the graph? So over here is -2. Another important point is 1, and then also 5. And so there's basically a maximum at x equals -2. So there's a maximum here. And at x equals 5, there's a minimum. So basically it's going to go, let me turn my pen off. It's basically going to go like this. And then right here is where the concavity has to change. So basically like this. Is concave down. This point, I should have actually put this lower. So nobody said I had to put it right there. So let me just erase that point and move it lower. Because the way this is going, it should look more like this. And then it hits the minimum. And then just try to smooth it out and make it look like a nice function. Okay, that's concave down. This part's concave up. And there we go.